How realistic is it that we will see airliners operating on pure hydrogen in the near future? As with any new technology, making this work will involve a lot of different challenges, and weirdly, the biggest one might not be to actually get the aircraft to fly on hydrogen. Stay tuned. Right now, there is a huge push in the aviation industry for a drastic reduction in aviation emissions. Part of that strategy has been to try and make existing aircraft more and more efficient, and as an example of that, the newer Airbus A320neo and the Boeing 737 MAX families are around 12 to 15% more efficient than their previous iterations were. And the Airbus A220-300, which is replacing some even older aircraft, will bring even better efficiency improvements than that. Now, we're still expecting even more progress from conventional aircraft through innovations like the CFM RISE engine, as well as from Boeing's and NASA's transonic thrust-braced wing project. Those are great steps in the right direction, but will still not be enough to move closer to a truly net zero carbon emission aviation industry. In order to do that, the aircraft and engine manufacturers are now exploring new solutions involving innovations in aviation fuel. The simplest option in terms of aircraft design involves Sustainable Aviation Fuels, or SAF. Essentially, SAF is very similar to regular jet fuel, but instead of crude oil, it's derived from alternate, renewable sources like waste products from existing crops, used oils, or even from dedicated crops that are planted for this purpose, like how we get biofuels for cars, for example. Right now, all existing airliners, including the 737 that I fly, can legally use a fuel blend that includes up to 50% SAF, but ultimately the goal is, of course, to increase that to 100%. Multiple tests have already shown that current jet engines would be able to handle this just fine, so why aren't we doing that already? Well, the reason that we have this 50% limit doesn't actually have anything to do with the engines in themselves. It has more to do with the aircraft's fuel system. As Björn Färm in Liham News explains in great details, aromatic hydrocarbons in conventional fuel help swell up the seals inside of the fuel tanks, pumps and the rest of the fuel system. Without these aromatic hydrocarbons, which doesn't exist in SAF fuels, engineers have to either redesign these seals or come up with new limitations for their use, like more frequent inspections and replacements, for example. However, to be perfectly honest here, this 50% limit of SAF is a bit, irrelevant anyway. And that's because there simply isn't enough of this new fuel to go around. The problem here is that not all methods of producing sustainable aviation fuels are really possible to scale up, at least not to anywhere near enough to use 50% of this stuff on a daily basis for an entire aircraft fleet. And of course, when a product is both scarce and in high demand, it also becomes very expensive. This, plus the fact that developing and certifying these fuels is a quite complicated process, means that SAF today costs several times more than conventional jet fuel does. Now, that price should drop over time as more and more is being produced, but it will likely remain significantly more expensive than conventional fuel for the foreseeable future. Also, there is worth noting that there are some other considerations when it comes to SAF as well. Everyone agrees that the production of these fuels cannot disrupt food production in areas where dedicated crops are used to make it. That's the reason why we can use the term sustainable aviation fuel instead of just calling it aviation biofuel. So, because of these scaling problems with SAF, the industry must also look for other solutions than that. And actually, there is another way to make SAF that could eventually become very scalable, and that's by capturing carbon dioxide from the atmosphere. But this process then involves combining CO2 with hydrogen. So, capturing carbon dioxide from the atmosphere and then combining it with hydrogen to make a new type of hydrocarbon would be a quite energy-intensive and complicated process. In that case, it would likely be more efficient to just use the hydrogen alone to drive the engines, and that's providing, of course, that we can figure out a way to do that. In order to make aviation successful and sustainable in the long term, focusing on next level efficiency and new innovations like this is going to be absolutely key. But For that to work, we need people to strive for excellence in what they do, and to find people who are curious and have scientific minds, willing to improve, and that's why I am so happy to have Brilliant as today's sponsor. Brilliant is an essential tool for professionals who want to sharpen their skills in STEM subjects like maths or computer science, which are both subjects that we need for this type of research. With its personalized and interactive learning approach, you'll be amazed on how much you can level up and improve in a very short period of time. One course that I highly recommend on Brilliant is Classic Mechanics, which is all about using core principles of physics to understand how matter in motion behaves. It covers everything from drones and rockets to skyscrapers and blinking fireflies. But if that's not your thing, then Brilliant also offers courses in data analysis, neural networks, AI, which is, by the way, very trendy right now, as well as loads of other subjects. So to get started for free for a full 30 days, check out brilliant.org/mentor now, or click on the link in the description here below. The first 200 of you who does so will also get 20% off Brilliant's annual premium subscription, which is great. So click on the link and start taking your first steps towards achieving your own new learning goals. Now let's continue. So, because of all of the current limitations in producing sustainable aviation fuels, we really need to look closely at the work being done to bring pure hydrogen into commercial aviation. And there have been quite some important developments around this topic during the last few years. A while back, I made a video over on the Mentour pilot channel about the Zero E program, which Airbus launched back in 2020. Back then, I explained that Airbus was looking at both of the two main ways in which hydrogen can be used to power commercial aircraft. So, what are these ways then? Well, the easiest one to explain is hydrogen combustion. This basically means using hydrogen to power gas turbines by igniting the gas inside a modified burn chamber. That's very similar to the way that we use regular jet fuel inside of jet engines today. Some modifications and adjustments to the engines will be necessary, but the engineers have already figured out how to replace jet fuel with hydrogen inside of gas turbines, so that's not really where the problem lies. Actually, the first time someone tried this was way back in 1988, when the Soviets used hydrogen to power 1 out of 3 engines on a modified Tupolev 154, which they then called the Tupolev 155. After the first few tests, the Soviets then switched their efforts to using liquefied natural gas instead of hydrogen in the same aircraft, but the tests did work, so it was definitely possible to do. So hydrogen combustion is the first way of using hydrogen to power an aircraft, but what's the second one then? Well, that's through the use of something called a hydrogen fuel cell. A fuel cell is a device that converts the chemical energy of a fuel, in this case hydrogen, into electrical energy without actual combustion. Essentially, a hydrogen fuel cell works by combining hydrogen gas in its molecular form, or H2, with molecular oxygen, or O2, from the atmosphere. This leads to a chemical reaction that produces electricity, water and heat. Actually, plenty of heat, which is part of the problem. The advantage of this method compared to hydrogen combustion, or the combustion of any other fuel really, is that the fuel cell can be much more efficient, getting a lot more energy out of a given amount of hydrogen. This electrical energy produced by the fuel cell is then used to run an electric motor that powers either propellers in the applications that are meant to replace turboprops, or fans for more jet-like applications. But if you watched the CFM Rise video that I made recently, you might remember that the design of turboprops and turbofans might actually be converging slightly in the near future, and the hydrogen fuel cell technology could benefit from this, allowing the engineers to focus on just one type of design. Right now, Airbus is actually busy modifying an Airbus A380 to use it as their first hydrogen flight test demonstrator. This aircraft will test both hydrogen combustion and hydrogen fuel cell technology, and to do this, Airbus will fit a pylon for a 5th engine on the upper left side of the 380's fuselage. The hydrogen combustion test will be done using a modified General Electric Passport engine, which is a smaller jet engine typically used on business jets. And for the fuel cell tests, Airbus is developing its own in-house propulsion system, and I'm really looking forward to see that one. This location of the test engine on the A380 away from its normal engines will allow Airbus not only to test the setups themselves, but also to do things like test the emissions that they leave behind. One worry with using hydrogen as an energy source for aircraft is that the process that creates that energy also creates a lot of water. Now, that might not sound like a big problem, but if that water is ejected at high altitude, it could lead to more dense contrails that would eventually spread out and form cirrus clouds. With thousands of aircraft potentially flying using this technology, this could potentially have detrimental effects on the environment, so studying these emissions is really important. Now, one reason that Airbus is using one single aircraft to test both hydrogen technologies is because that enables them to use the same fuel supply, storage and other experimental equipment on both. And that brings us to the issue of fuel storage. Obviously, to use hydrogen safely, we have to figure out a way to store it and then move it through the aircraft towards the engines, and here is where things start to get really tricky. As I've said many times before, weight is always the enemy in an aircraft design. And the great news here is that for the given amount of energy, hydrogen has only around 1/3 the weight of jet fuel. However, the bad news is that hydrogen is a lot less dense, which means that it needs 4 times the volume of jet fuel to extract the same amount of energy. So this means that we need a lot of room for the fuel on a hydrogen-powered aircraft. Plus, we have to find new places to store it because we can't simply put hydrogen inside of the wing like with regular fuel. So why is that then? Well, it's because the hydrogen must be stored in thermally insulated tanks at extremely low temperatures so that it remains in its liquid form. How cold, you might ask? Well, for it to remain in its liquid form, hydrogen needs to be at around 20 degrees Kelvin, or in other words, 20 degrees above absolute zero. That's minus 253 degrees Celsius, or minus 423 degrees Fahrenheit. Theoretically, we could pressurize hydrogen instead, but this would create other problems, like the need for an even heavier tank to withstand and hold the pressure inside. Hydrogen is the smallest chemical element that we know of, which makes it difficult to keep sealed in any container of any sort, as it just seeps through most materials, and that's especially true when it's kept at high pressure. In the Zero E aircraft that Airbus showed during its presentation back in 2020, they had several different designs, but among the more conventional looking ones, the tank was situated in the back of the aircraft's main cabin, and it was equipped with a small mast protruding from the vertical stabilizer, supposedly to enable the venting of hydrogen gas in the case of a leak. That same mast was actually also present on the Soviet Tupolev 155. Fortunately though, Airbus and others in the aerospace industry have been working with liquid hydrogen for quite some time now, and they know how to deal with it. And that's because the rocket engines of many space vehicles often run on liquid hydrogen and liquid oxygen. These vehicles include, for example, NASA's Space Shuttle and the Ariane 5. The Ariane Group is a joint venture between Airbus and the engine maker Safran, so Airbus will draw heavily on Ariane's experience to develop the technologies they need for hydrogen fuel tanks and also other related systems. But of course, developing hydrogen tanks that will remain in service for the lifetime of an airliner is a challenge that space launch vehicles don't have to deal with. Oh, and by the way, if you're interested in what SpaceX uses for their reusable rockets, it's not hydrogen. They instead use a type of rocket-grade kerosene, which is actually very similar to jet fuel. Now, the volume needed for the hydrogen tank is another reason why Airbus went with the A380 as its flying testbed. The easiest way to store it is in a spherical tank, but that's likely something that will need to be worked out before this technology becomes commercially viable. Airbus will use the very first A380 ever made for this task, because that aircraft is already configured as a test aircraft, and it also lacks a normal cabin interior, giving it plenty of space for the tanks and other systems that Airbus needs to fit in as well. So figuring out where and how to store and transport hydrogen, creating fuel cells and combustion engine technology is all quite complicated, but like I mentioned in the very beginning of the video, the biggest problem with making this happen might actually be something completely different. Because of the sheer volume of hydrogen needed, we probably won't see this technology used on long-haul aircraft, at least not for a while. And this means that in the beginning of a fully sustainable aviation industry, those big jets will have to rely on sustainable aviation fuel, while hydrogen will have to handle short to medium haul aircraft. And of course, that means that there needs to be a steady flow of reliable hydrogen supply to every single airport in the world where aircraft might need to use it. And on top of that, it must be green hydrogen, meaning that it must come from renewable sources. Today, nearly all hydrogen is made in other ways, for example, as a byproduct of various petrochemical processes. Now, as an element, hydrogen is ubiquitous. Wherever there is spare electrical capacity from renewable sources, we can generate hydrogen as long as water is also available. But creating the kind of infrastructure that will bring this fuel to airports and then also permit it to be safely stored there is going to be a big challenge. It will require an enormous effort from aviation and airport authorities, academics, as well as research institutions and industry around the world. All of them will have to work together to create the kind of infrastructure similar to what we have for fuel today needed to make this work. Now, the good news is that there already exist organizations like the Hydrogen Council who is working towards this goal and who have actually been doing this for several years. The members include world leaders and tech titans who have been discussing ways to make this happen, and it's actually fascinating that their work haven't received more attention. I'll link to their website in the description below. Airbus is working with several partners, including the Hydrogen Council, to building what they call a hydrogen hub at airports, which, if it works, could make all of this possible. Airbus believes that getting this infrastructure in place by 2035, when it expects the first hydrogen-powered airliner to enter service, is possible. But they also say that it will probably take considerably longer time than that to make this technology available at every airport worldwide. So that all sounds interesting, expensive, and really complicated. Are there any other options out there? Could there maybe be a better, simpler, and faster way to make hydrogen widely available at airports? Well, the people behind a company called Universal Hydrogen certainly thinks that that's the case. On the 2nd of March of this year, 2023, Universal Hydrogen's Dash 8 300 flight test prototype took off for the very first time. Its right turboprop engine was replaced with a fuel cell and an electric motor setup, and that was then being fed hydrogen from a tank inside of the main fuselage. The first flight was relatively short around Grant County International Airport in Moses Lake, Washington, but it was still a monumental achievement. The aircraft took off using the turboprop on the left and the fuel cell powered electric motor on the right, and the pilots then throttled back on the normal engine and flew mainly on the hydrogen fuel cell propulsion to test out how it would handle. The flight lasted around 15 minutes and then landed perfectly safely. So far, that Dash 8 is the largest hydrogen-powered test aircraft that has flown, a part of course, that Soviet-era Tupolev 155. Universal Hydrogen and its partners ultimately want to offer conversions for the Dash 8 and the ATR 72, and whilst the Dash 8 flew first, the ATR will probably be the first one to enter commercial service. But what we should be focusing on regarding Universal Hydrogen isn't really the aircraft or the hydrogen-driven fuel cell. They aren't really interested in building the propulsion system. Instead, they are going to partner with other companies to do that. No, their project is all about creating the hydrogen infrastructure, which in their idea revolves around the fuel tanks, which are removable. The analogy that Universal Hydrogen is using to describe their idea is, well, the coffee capsule. They have stated that they want to become the Nespresso company of hydrogen, since Nespresso never really made any coffee machines. They licensed the name and partnered with companies who made those. Instead, their business model was all about selling the coffee capsules. That's what Universal Hydrogen wants to do as well. They aim to design and certify a cryogenic hydrogen tank, which will fit through a big cargo-style door on the side of the aircraft fuselage. Between flights, ground crew will be able to use standard airport equipment to swap tanks, which are referred to as hydrogen capsules. Crucially though, these capsules could also be used by other machines and vehicles at the airport, but really anywhere. If they prove to be practical, these capsules will eliminate the need to create extensive hydrogen infrastructure at the airport, or At least these hydrogen capsules could make the creation of this infrastructure a bit less urgent. Now, you might think that Universal Hydrogen's idea is competing with Airbus efforts to create an airport hydrogen hub, but that's not the case. On the contrary, Airbus is actually investing in Universal Hydrogen through its Airbus Ventures arm, and Paul Eremenko, the CEO and co-founder of Universal Hydrogen, previously worked as Chief Technical Officer at Airbus. The topic of aviation hydrogen propulsion, its challenges and the great work that a lot of people are investing in it is enormous. This video only scratches the surface, and I will come back to this topic later on as the technology evolves. If you're interested in learning more right now, I highly recommend you to check out Björn Färm's and Scott Hamilton's work in the links here below. It's really fascinating. Oh, and one final thing. I know that quite a lot of you are typing something in the comment section right now about Hindenburg, right? Now, without getting into too much detail, Hindenburg used unpressurized hydrogen at normal temperatures stored in fabric tanks. That was pretty low tech even for 1937, so it wasn't really a huge surprise that that accident finally happened. Let's just say that we've learned quite a bit since then. Yes, hydrogen mixed with oxygen is a dangerous combination, but not when it's properly managed and controlled. Remember that we are currently storing kerosene in aircraft wings, and we then feed it through pipes, pumps, valves and injectors, burning it out in the back of the jet engines. And we're doing that perfectly safely with tens of thousands of aircraft flying every single day. Figuring that out wasn't straightforward either, but we did it, and we absolutely can work it out again, hopefully much faster with hydrogen or whatever new propulsion innovation might come next. I hope that I've earned a subscription and a like from you, so check out this video next, and if you want to support what I do here, then consider sending a super thanks, buying some merch or joining my fabulous Patreon crew. Have an absolutely fantastic day, and I'll see you next time. Bye bye.